Hi everyone, my name is Dixon Cuadros from Potencia y Tecnologías Incorporadas PTI. Today I'm going to talk about the application of intelligent load sharing system in a wastewater treatment plant. The agenda of this presentation begins with the Aguas Claras project overview. Then we're going to talk about the general data and we'll give you a description of the operation of the wastewater treatment plant, emphasizing the main challenge that involved the operation of the critical load and the social environmental impacts of the project. Later, we're going to show ETAP ILS as the solution, presenting the system architecture and its operation. Up next, we will look at the benefits of ETAP ILS and demonstrate how this protects the continued critical operation of the power system. Finally, there will be a space to recognize the project collaborators. Well, let's start. The Aguas Claras wastewater treatment plant is located at Bello, Colombia. The project, inaugurated in 2018, has an estimated cost of 1.6 billion of Colombian pesos, approximately $45 million, and was constructed in a 45 hectares lot. The average design flow of the plant is 5 cubic meters per second, but the maximum design flow is 6.5 cubic meters per second. The plant has the capacity of remove 140 tons of sludge per day, and with the thermal drying plant, they can dry 400 tons of sludge per day. The EPM Group is the owner of the project. EPM, parent company of the EPM Group, one of the largest utility companies in Latin America, carry out technical and administrative management for the construction, testing, and commissioning of the plant. Aguas Nacionales, a subsidiary of the EPM Group, is the owner, operator, and maintainer of the Aguas Claras wastewater treatment plant, hereinafter WTT. The power system of the Aguas Claras WTT has a design load of 13 megawatts. Its operating load is a maximum of 10 megawatts and may vary throughout the day. The plant generation units include 6 motor generators located in the energy recovery building, 2 turbo generators located in the thermal drying plant, and 2 connections in parallel to the Bello substation at a voltage of 46 kV. All of this allows the plant to generate between 0.9 megawatts and 13.9 megawatts of electrical energy for self-consumption and export energy to the national interconnected system. Before entering into the main challenge of the project, it is necessary to know the operating principle of a WTT. In this graph, we will see step by step the wastewater treatment process. Let's start with the preliminary treatment. Here, we have a structure of bars of different sizes where the removal of the garbage and large element is carried out. Then, there are sand traps that allow the sands to be separated from the wastewater. Finally, in this step, the main pumping of the process also occurs. This is the only pumping in the water line. Then, in the primary and secondary treatment, the wastewater flows by gravity. In the primary treatment phase, the sedimentation of the sludge occurs, reducing the flow of wastewater in the sedimentation tank. This process allows the separation of the sludge from the wastewater. The primary sludge undergoes an additional treatment that we will explain later. In the next step, the wastewater reaches the secondary treatment, where the activated sludge treatment takes place. This is the most critical process of the entire water line, because it is a biological process that uses microorganisms to carry out the removal of biodegradable organic matter. As a result of this process, we obtain the treated water that is returned to the river, and the secondary sludge that goes to the sludge treatment together with the primary sludge. The sludge treatment process consists of stabilizing the sludge removed from the wastewater. This is done through a digestion process that lasts up to 20 days, where biogas and stabilized biosolids are produced. The stabilized biosolid is dehydrated and taken for its final disposal. The biogas is used to feed the headlines necessary in the process and to generate energy through the 6 motor generators available in the plant. This is the energy recovery process. Finally, the stabilized sludge from the digestion process is taken to the thermal drying plant, where the biosolid is thermally dried using the thermal energy produced by 2 turbogenerators powered by natural gas. Let's get closer to the activated sludge process. This is a secondary treatment that we have just explained. As we see in the image, the wastewater enters the aeration tank, where the microorganisms feed on the organic matter on the surface, converting the dissolved organic matter into simpler elements such as new bacteria, carbon dioxide, and water. Then, in the secondary sedimentation tank, the activated sludge is collected, returning part of it back to the aeration tank in order to maintain the necessary level of microorganisms in the tank. The microorganisms that live in the aeration tank need a specific concentration of oxygen to survive. This is why a blower system is responsible for injecting oxygen microbubbles into the tank, keeping the microorganisms alive and therefore keeping the process running. For this reason, the blowing system is a critical load that we must keep in line at all times. Other critical loads are the odor control system that prevents odors in the preliminary and primary treatment. Let's now see the importance of proper odor control in the plant. On this map, we find the area surrounding the Aguas Claras wastewater treatment plant. As you can see, most of the buildings around are urbanizations and shopping centers, where the comfort and health of the inhabitants of the area is the important thing. On the other hand, the UBA Aguas Claras is one of the 14 articulated life units of EPM, a place to learn, to play, a space where homage is paid to nature and the families have the opportunity to share free time and enjoy cultural events. For this reason, the plant cannot produce bad odors that pollute the air in the area. Therefore, to ensure the continuous operation of the critical loads in the system, the ETAP intelligent load sharing system was implemented in the Aguas Claras WTT. Let's take a look to the system architecture. For the implementation of the system, all the information of the protection relays, variable speed drives, soft starters, power factor controllers, power quality meters, circuit breakers, uninterruptible power units, automatic transfers, and other devices was integrated into the ETAP RT system via an Schneider OPC server. The data is stored in a historical database which is consulted in real time by 2 workstations, which have human-machines interfaces, HMIs, which facilitate the interpretation of the data in the one-line diagram or through personalized graphics. On the other hand, an ILS servers perform the logical processing of the data to predict the behavior of the system in case of loss of any of the available energy sources. A trick command list is loaded to the master PLC continuously. The PLC waits a power loss event. When an event happens, the PLC immediately operates on the selected load breakers by ILS to remove what is necessary to maintain system stability. The ILS server has a redundancy server, which can act as an emergency or maintenance backup for the main processing server. Downstream, the system communicates with the 17 process substation trucks near the CVAs, which are responsible for exchanging information with the equipment to collect data in real time, generate opening and closing commands, as well as tripping in the case of load sharing. For the calculation, ETAP ILS takes into account the loads to be shed that are in service and whose breaker is enabled for tripping. On the other hand, the system monitors the generation of the power sources to define, based on its list of priorities, the loads to shed due to the loss of any of the power sources. Let's take a look at this example of how ILS works. First, the output of one of the energy sources of the system occurs. ETAP ILS, prior to the event, has already loaded at least trip of the master on the master PLC. So this device, upon receiving the trip signal from the power source, sends the sharing command to the corresponding loads to restore the stability of the system, with the balance between load and generation, while the critical load is kept online. Let's see the operation of ETAP ILS in our Claras power system. Here the system is operating in island mode, with 3 motor generators online as the only power source. All the process is online, excepting the blower system in red. The ILS monitor in the right side of your screen is showing the calculation of the requested load to be shed, based on the generation of the 3 power units and the consumption in real time. The list of trips is sent to the master PLC, which is waiting for one of the available triggers to send the trip commands and the loads that are going to be shed during the event. You can see the scratch table at the top left side of your screen. Now let's see what happens when the event occurs. The loads are shed by the PLC from the system according to the trip command list. Then ILS calculates the new requested load to be shed based on the generation of the power units that are still online and the new available loads. The offline loads can be restored depending on its control mode and interlocks. Now, let's get closer to the operator view. Here we have all the green loads offline, but the critical process is still at the same time that 2 motor generators are supplying the power that the system is requesting. For the restoration of the system, the load in red are loaded by the PLC logic, and the other loads are available for being restored. With the implementation of ETAP ILS, the Aguas Claras WTT can minimize the risk of tripping critical equipment, such as the blowing system or the other control system. This will be help prevent the emission of bad odors in the plant, in addition to preserving the necessary concentration of microorganisms in the secondary treatment of wastewater. Other benefits of ETAP ILS allows the Aguas Claras WTT to avoid unwanted blackouts, facilitate the transfer of circuits for the maintenance of lines and transformers, and increase the flexibility of the power system during contingency or emergency conditions. Finally, in this space, we want to present the companies that have collaborated with the implementation of the system and that have currently completed the integration of the thermal drying plant. EXDCI from Spain have carried out the configuration of the PLCs, CVAs, and the communication for the integration of the signals. The data execution, relays, and meters are Siemens, as well as the process PLC at the thermal drying plant. Schneider Electric is the provider of the infrastructure of the rest of the plan that includes the CVAs, PLCs, and the communication to the ETAP real-time ILS server. ETAP is the provider of the ILS servers, workstations, historian server, and analysis software. They have designed the ILS system logic and all the ETAP real-time software configuration on the machines. PTI has collaborated in the design of new HMIs for the system, the integration of the signals from the thermal drying plant, and the support on site for test and acceptance. Thanks everyone for watching. Now I will be available to answer your questions about the presentation.